So first we open Audacity, close the splash screen, open the data file, and here it is, the WAV file is displayed. That's a reference tone. Okay, we're going to remove some of that stuff we don't need. The first thing we're going to do is we're going to look at the spectral content of this guy and find the natural frequency of that tone we hear. So we select three of the apps. We click on Analyze Plot Spectrum. And if you want the frequency, if you want to have good resolution of frequencies below 100 hertz, then you need to crank up the sample size because you need a lot of samples for low frequency things because it takes a lot of samples to resolve the low frequency because it's fairly slow changing. So we'll go to 8,192 and it gives us some resolution. Okay, so right here we see a peak. That's probably our fundamental. So we place the cursor around there, and what you see is over here the peak. This tells you what the center of the peak that the cursor is near, and it's 105 hertz. The cursor is actually located about 108 hertz. So you need to look at this peak thing to know what the resonant frequency is. So in this case, it's 105. So that's the key bit of data. So we'll record that in our summary spreadsheet. The next thing we need to do is to generate a waveform that we can feed into Excel. So let's do that. And we see it right there. You can see at the beginning of the plunk, there's lots of distortion. Right around in here, we start getting what looks to me to be pretty good data. So we'll take that data and now we'll send that data to a file. So to do that, we go Tools, Sample Data Export. So our highlighted stuff is going to go. And on the header, we're going to use the standard header because that will label this guy. And over here, it says black walnut with sensor. So that's good. So that's labeled for the file name. And then we'll call it black walnut sensor 3. We'll record a new file and we'll hit we want to make sure the measurement scale is linear and not decibels because that would be real confusing. And then we hit apply and it's done it. So now let's go look and find that file. Documents, Audacity, black walnut, highlight it, selects everything, hit copy. Okay, and now we want to go to Excel. Wood damping test data. I don't know what. Okay, now we want to paste the data that we had from that text file. So here's that text file. Here's this stuff. Verify we've got it in the copy buffer. Copy. So we'll go practice paste right here. Control V. So here's the data right there. Control Shift, arrow down. Get it all cut. So this is the time, and if you look up here, the sample rate is 44,100 samples per second. So each time step, we take the previous time and we add 1/44,100th of a second to it. So that's what this calculation is doing right there. We'll just copy that calculation down so that will index time. And then over here, we have a simulated waveform. So we have a sinusoidal portion and an exponential decay portion. And the sinusoid is at 105 hertz, which is what we measured for the frequency of that guy. So we're going to be simulating this waveform, and you'll see that here. That'll become more obvious. So let's go ahead and copy this down to the end of the data. Excel tricks. Okay, now we want to graph this and see how it looks. So we select all the data. We go to Insert, Scatter Graph, Lines. There it is. Let's cut that. Put it up to the top where we can see it a little better. That's helpful for when we go to manipulate this stuff. Paste, Control V. Oh, here's the graph. Now the orange thing here is the second series, this series right here, which is our simulation. The blue, which you can sort of see behind there, is the actual data. So I need to make the orange a little smaller in amplitude. This constant controls the amplitude. Okay. So now this controls the amplitude, this controls the decay constant. So here's the time, here's the decay constant. This cell right there is decay constant, so we want that. That's all that math is good. So now we want to increase the amplitude. So we'll go from 0.25 to looks like maybe 0.8. That'll scale that orange upward. So that's closer. Let's make this graph a little bigger. Okay, so looking at this over in this area, we need to make our constant a little bigger here and our decay perhaps just a smidge faster. So we'll change the decay constant to 6 so it decays faster. And we'll change the sky to 0.9. You make this a little bigger again, 0.95. Okay, that's a pretty good match. So you see this thing decays away at about the same rate that this guy falls off. So I'm happy with that. So we think our decay constant for the for this black walnut specimen is about 6. Okay, so we go to the summary table. And we see that decay for black walnut is 6, and the frequency is 105. Okay. And black walnut, make it 105. Okay. So this has then allows us to calculate the modulus based on the frequency response and the density of the material. And we see that for black walnut, the modulus is fairly low. For white oak, it's much higher. For crabapple, it's much higher. For Osage orange, it's a bit higher. It's surprisingly low. Right? We had expected sage orange would be a bit stronger than that, but it's not. Surprising, but it's what we measured. So here's our data, and I've gone through and I've calculated decay constants for these various things. Hackberry decays really fast, so its constant is 19 compared to 6 for black walnut. Crabapple 17, cherry is 12, magnolia or spruce is 9, magnolia is 8, white oak 7, sage orange 6.5. But when I have previously ranked materials for using them in ukuleles, I've ranked them based on the modulus and the density. So high modulus is good, um, low density is good. So I take to get a ranking, I would take the modulus and divide it by density. So over here, we have a graph that ranks materials based on modulus and density. And when you look at that ranking, then you see that spruce, cherry, crabapple, and hackberry are all pretty good stuff. Magnolia is not as good, and Osage orange is not very good because it's so dense. And black walnut is not so good based on the modulus that we measured with these lung tests. But now, if we take into account we include the effect of damping, so that damping being kind of bad, then the rankings change around a little bit. Number one is white oak, which has low damping and pretty high modulus and reasonable density. So number two is black walnut. Number three is spruce, which I've never used, but is commonly used on ukuleles. According to this, white oak should be as good as, and black walnut should be as good. Then would come cherry, but it's pretty far below black walnut and white oak. And then would come crabapple, which I've made many ukuleles from that sound kind of okay. And hackberry, which I've never used, but I have some. It would be a poor choice for a frontwood. And here we see magnolia is not not the worst choice, better than crabapple. And Osage orange would be an okay wood, but it's very hard to work, and I don't know that you could actually make a ukulele front from it without great difficulty. But surprising winner is white oak. Surprising and yet not surprising. The ukuleles I built for Quinn and Thomas from white oak sound really good. The ukulele I made for David has a white oak front, and it sounds quite good as well. So this was enlightening. A dark horse kind of emerged from behind. Another learning from this testing was that previously I've used values for modulus that I have got from the wood database. And the wood database is great, but the test specimens there may not be oriented the same way that I orient things. Everything I tested, I had precisely quarter sawn, which is was what I try to do when I make a front for a ukulele. And quarter sawn wood may not have quite the same stiffness as flat sawn wood. And so most of the data in the wood database may be for flat sawn wood. I wouldn't think that it would be all that much different, but my results here suggest that it may be that different. So there you go.